Hey gang, welcome to the Weather Breakdown channel. In this video, we're going to talk about jet streaks, those fast-moving pockets of air within an existing jet stream, which actually play a very crucial role in meteorology. We'll talk about how they are formed, the exit and exit regions of a jet streak, and their implications on the large-scale vertical motion within the atmosphere. Now, this is my first video, so things might not go as smoothly as I would want. Now, practice makes perfect, so I'm hoping that future videos might go a little bit smoother than this one. Now, all things considered, if you would still like the video, feel free to press the like button, and let's kick things off and see what jet streaks are actually all about. To understand what a jet streak is, we must first identify what a jet stream is, since a jet streak is a faster moving portion of air within an existing jet stream. Now, the jet stream itself is pretty easily visualizable using the following concept. Say you have the globe here with the North Pole here, South Pole here, and equator here, right? Near the equator, you have warmer air than you have near the poles. And what nature tries to do, it doesn't like any imbalance at all, so it tries to eliminate it as fast as it can. So it tries to move this air northward into a straight line towards the poles. Okay, but the Earth is actually a rotating sphere while this motion is ongoing from the equator to the poles. So because of the Earth's rotation, there's a force acting on this wind, which is called the Coriolis force. And that Coriolis force in the northern hemisphere acts to deflect this northward motion to the right. Okay. And since this is a perpetual process where wind is moving from the equator to the poles and the Earth never-ending rotating, the Coriolis force acts perpetually on it as well, meaning that essentially or eventually there's a balance between these forces, and this balance is called the Geostrophic balance, right? And this balance acts to create a ring around the poles circulating the globe at high altitude, say 10 to 12 kilometers above the surface at high speeds, separating a colder air mass in the poles from a warmer air mass near the equator. And this ring of air is what meteorologists refer to as the jet stream. All right. Now, since this jet stream separates a polar air mass in the north from a more tropical air mass to the south, this jet stream is aptly labeled the polar jet. Okay? Now, you might think that it's temperature that's driving this wind northward from the equator to the poles, but that's not really the case, which leads us to one of the most fundamental principles in meteorology. And that fundamental principle states the following: a difference in temperature drives a difference in pressure, and it's this difference in pressure that's driving the wind, right? So in order to fully understand how jet streaks work, we must first start to look at this middle term here and how it plays a crucial role in the initiation of horizontal motion within the atmosphere. We've talked about the polar jet, right? Separating the polar air mass in the north from a more tropical air mass to the south. This is just one of many jets. You have the polar jet circulating at 12 kilometers high above the surface. Then you have the mid-latitude jet circulating at more or less 6 kilometers high above the surface. And then you have the low-level jet moving over the Earth at 1.5 kilometers above the surface, right? These are just 3 levels of jets that I can mention: upper level, mid-level, and low level. Now, we've also talked about not being the temperature that's the driver for the motion from point A to B, but it's the pressure difference that arises from the temperature difference that's responsible for the horizontal motion from point A to B. So in our further section of the video, we're going to talk about how that pressure difference is actually responsible for initiating the motion in something that is called the pressure gradient force. Now, meteorologists, they like to work in layers, right? So if you draw, for example, a diagram with the y-axis representing increasing height, the more you go up into the atmosphere, right? Starting from 1000 millibars, or what's actually called the surface level, right? And you draw on the x-axis, for example, 2 points separated horizontal distance from each other, say point A and point B, we can illustrate the following. In meteorology, the average temperature of a layer is directly proportional to the vertical thickness of that layer, right? Now, this equation is called in meteorology the hypsometric equation, right? And we can illustrate this as follows. Say, for example, near point A, we have a certain thickness from 1000 millibars to 500 millibars, right? So a certain thickness from 1000 millibars to 500 millibars, all right? Now, at point B or near point B, it's actually warmer, or the average temperature in that layer is warmer. This means that if you draw a vertical line to that layer, right, the average temperature is higher than here. This means that the 500 millibar level, right, has more thickness, right? So this means that if you draw some labels here, we have the warmer air mass here. It's warmer here, right, occupying more space than the colder here on the left, right? Now, if you think about it from a visual perspective and look at it visually, right, you can see that if you draw, for example, an isoline for the 500 millibars, you can see that this isoline starts to slope downward from the warmer air mass to the colder, right? And there's a few observations we can do here, right? If you really think about it now, the 500 millibar level in the warmer air mass is situated higher above ground, right, than the 500 millibar is. There is a delta here. This is observation number one, right? Observation number two is, if you look at it here arbitrarily along this line, you can see that here the pressure is relatively higher than it's actually here, right? Now, this means that since the air horizontally has a higher pressure here, lower pressure here, air tends to move from high pressure to low pressure. This means that there is a pressure gradient force driving this wind horizontally from high to low, right? This is what's called the PGF, horizontal. So the horizontal pressure gradient force, right? Because remember what we said in the previous section of the video, it's not really the temperature directly that's responsible for the motion. A difference in temperature creates a difference in pressure, and it's this difference in pressure which drives the wind, right? So now we arrive at our conclusion here and why this term is so important and how it drives the wind. This difference in pressure is driven by the difference in thickness between the warmer air mass and the colder air mass, which is called the hypsometric equation, leading to a vertical slope of the 500 millibars, which in turn leads horizontally to a pressure gradient force moving air from high pressure to low pressure, from the warmer air mass to the colder. Now, if we take our diagram and start to apply it to a real case scenario, you can see the following. Say, for example, this chart here. This chart shows yellow contours, and the yellow contours are actually the 1000 to 500 millibar thickness in meters, right? Or geopotential meters, as it's called. So as you can see here, this value here, you have a thickness of 4,900, which is a lower thickness, compared to the thickness here, which is 5,750 meters. The thickness here is more, which means if we follow the hypsometric equation, right, there should be a warmer air mass here, right, than there is here in the center where it's colder. We've also identified, because of this thickness, the 500 millibar level slopes downward, which you can easily see by these values: 5,100, 5,750, 5,700, 5,650, and it slopes downward towards the colder air, right? And because of this sloping down, there is, if you remember, a higher pressure here on a constant height level than there is here, a lower pressure. And because of this difference between high pressure and low pressure, there's a pressure gradient force trying to move this wind in a straight line from high to low. But we've also identified in the beginning of the video that the Earth is a rotating sphere. And we've identified that this wind going from warmer to colder in the northern hemisphere, because of the Coriolis force that acts on it, starts to be deflected to the right. And you can see the same thing everywhere. There's an air parcel here. It moves perpendicular to the height contours along a sloping 500 millibar level to the colder air mass. And this airflow is also deflected to the right. You have the same thing here. Air parcel here tries to move perpendicular to the height contours along a sloping 500 millibar level towards the lower pressure. But this one gets deflected to the right. And you can see this everywhere. Take an air parcel here, is the exact same story. It tries to move perpendicular to the height contours along the sloping 500 millibar level towards the low, but it also gets deflected to the right because of the Coriolis force. Now, the steeper the gradient is, and the closer the warmer air mass is to the colder, and the higher the difference is, the steeper the slope would be, and the faster the wind will go, meaning this air parcel in a more or steeper sloping gradient will start accelerate faster towards the lower air than here. And you can see this here. These contour levels are further apart from each other than here, meaning that this portion slopes more steeper than this one. So air starts to flow from here to here slower than it starts to move from here to here, right? Because of the gradient, okay? Now you can see the same thing here. You have a warmer air mass here, you have a colder air mass here. It tries to move in a straight line that way. Coriolis acts upon it and deflects the wind to the right. And if we really start to look at it, this means that because of the gradient being greater here, closer together here than it is here, and then it is here, there should be a wind maximum here where the deflection happens, moving along the 500 millibar contours in a parallel sense. You can see the same thing here. Essentially, the gradient is greater here than it is here, meaning that the wind speed should be faster here than here, and the wind gets deflected to the right. So there should be, in theory, a wind maximum here in this direction. Here it is in this direction. Here it is in this direction, here like this, and here like so, right? And the thumb rule is, with the wind in your back, right? With wind in your back, lower height will be to your left, okay? And we can prove this actually, that there is a wind maximum there, because if we toggle on the maximum wind here, you can really see that there is a perfect correlation between the theoretical explanation and the reality is. So we can see actually, if you have a sloping 500 millibar height chart, the steeper the lines are together, the faster the wind is. And the wind, as you can see here, is blowing parallel to those height contours. And this wind has a specific name. And that name is called the Geostrophic wind. And why it's called geostrophic? Well, it's not too far-fetched, because we already know that wind is moving from high to low pressure. It gets deflected to the right by the Coriolis force. And if you remember, there's a balance between these forces. And this balance is called the geostrophic balance, right? Which is why it's called the geostrophic wind, because it's the wind created by the geostrophic balance that created because the Coriolis force tries to deflect the wind going along a sloping 500 millibar line from high to low to the right, leading to the wind maximum here, which you can also identify by the thickness contours being closer together. If you would like the video, feel free to press the like button or drop a comment in the comment section to share with me what you think was good about the video. Also, potentially share with me what you think can improve in the future, because I'm planning to release more videos in the future. So if you want to be notified of those videos, feel free to subscribe to the channel so you can get notified whenever I upload some new content. And this new content can be varied. It can be a meteorology concept that I explain, such as this one, or it can be a forecast when a specific weather situation develops or starts to impact Europe. In the previous section of the video, we've uncovered what a jet stream is, how it's formed, and how you can easily see it on a 500 millibar height chart, as you can see here, right? This is what's called a jet stream, right? A faster moving portion of air than its surroundings. But the jet streak is actually a accentuated portion within that jet stream where the gradient between the 500 millibar height contours, meaning the steeper slope here of the 500 millibar isoline, is greater than anywhere else in the jet, leading to an accentuated region where wind speeds are higher in the jet. This is what's called the jet streak. Jet streak itself has a maximum wind in the center, while it's gradually to the sides decreasing in intensity, right? And we've also identified in our previous section that due to the sloping 500 millibar line, the air tries to move from high to low pressure if you consider a constant height chart, right? It gets deflected to the right because of the Coriolis force, right? And this means that as air tries to move here and gets deflected to the right, it enters from here the region where the wind speeds are maximum. This region is called the entrance region of a jet. Here. This is the entrance region of a jet streak, right? And you can have the same thing here as air, right, moves away now from the center, it slows down, right? And as air moves out of the maximum here, there's another region that we can consider, and this is the exit region of the jet here, where wind exits the maximum wind intensity. Okay, and now we're going to look at these two regions here, the entrance region and the exit region, because they play a crucial role in the initiation of vertical motion within the atmosphere. We consider our entrance region here in the jet, right? Let's recapitulate a bit. There's a warmer air mass here, there's a colder air mass here, right? Air tries to move along the sloping 500 millibar line towards the colder air mass, but Coriolis force acts on it and deflects that airflow to the right, leading to the wind maximum here, right? So the Coriolis force, as we've already identified, is responsible for that, right? Now, if we start to look at this entrance region a little bit deeper and how it results in vertical motions, either upward or downward, we can draw a cross-section here, right? And we can see some interesting things. So let's draw this cross-section here from point A to point B. So this is point A, this is point B. And if we draw our cross-section, for example, right, this is the 500 millibar height, right? This is 1000 millibar here at surface, okay? And we separate these points here, A and B. Say, for example, here A and here B. Right? Let's talk about it again. So air tries to move from here to here, right? But Coriolis force deflects that portion to the right. Okay? Since the air, this means that initially the air is moving from here to here, right? Along this line from A to B. But due to this deflection, this airflow does not occur, so let's erase that airflow, okay? What's actually happening is air tries to move here and it gets deflected to the right, meaning air is actually disappearing here. At point A, 500 millibars, there's air disappearing, right? And since this air is disappearing and is deflected, right, there's actually a diverging motion here happening at point A, meaning there's air diverging here, right? It disappears and it gets deflected, meaning there's a divergent air aloft here. Now, this diverging airflow sets up a whole avalanche of motions, right, within the atmosphere. And these motions are as follows. Since there's air disappearing and diverging here, there's air filling that up here from the ground, meaning that at point A, at surface, there's actually vertical motion, right, trying to replace this air here. But since this air, right, tries to move upward, there's air here, there's a secondary circulation that's initiated trying to fill that void up here. So since air is now disappearing here, to rush here, converges with the airflow here and pushes this air up to fill in the divergence, right? There's air disappearing here, meaning there's a diverging airflow here now, right? There's air diverging here, converging with this one, pushing this one up to fill in the diverging airflow here. And because of this air leaving here, there's a sinking motion here at B, 500 millimeters high above the surface. There's air sinking here to fill in the diverging airflow here. And you can see the proof of that diverging air, or of that sinking air rather, downward, if you really look at the brightness temperatures here in the satellite imagery. There's a brightness temperature here that's colder, meaning darker, than here, where it's actually, where you can see upward vertical motion. Why upward vertical motion? Yeah, it's pretty evident here by the thunderstorms that are present here. So this air sinks, leading to the darker brightness temperatures in the satellite imagery, right? So you can see this air here sinking downward because this air is diverging to fill in the void here, converging this flow here, pushing this one up to fill in the divergence aloft. So what you can actually see now is the right entrance region. This is the right entrance region, right? And this is the left entrance region. Okay, the right entrance region is an ideal location to start look for upward motion. Okay, and if in this upward motion the air is buoyant enough and there's gape and instability, right, it's an ideal location to look for the initiation of thunderstorms, or the strengthening of existing thunderstorms, right? Or regions to look for precipitation, all right? So we've now identified that the right entrance region of the jet, right, is where you would see vertical motion from the surface up to the high levels, okay? So we've now identified why the right entrance region of the jet is an ideal location to look for vertical motion within the atmosphere, right? If there's gape there, instability there, it can lead to thunderstorms because of this upward vertical motion filling in the divergence aloft, okay? So we've now covered the entrance region, but what about the exit region? Now, if we consider the exit region of a jet here, this region, okay, you can actually see the following. Say this here, you have the wind maximum here, right? The wind maximum is moving parallel to the 500 millibar height contours. And we've identified in previous sections in the video that the wind is moving along these isolines because of the geostrophic balance, right? The balance between the wind speed and the Coriolis force, right? So wind speed and the Coriolis force. Okay. Now, if you consider the following, since air is actually exiting the jet streak, right, it actually starts to slow down, right? And we must consider that Coriolis, it's a force that starts slow and stops slow, meaning that as air exits the jet streak, right, wind speed decreases, right, but Coriolis is slow to respond to this wind speed, leading to no longer a balance but an imbalance in the geostrophic balance, right? And it's this imbalance that makes it so that due to the decrease in wind speed, there's Coriolis, as we all know, it deflects. If air moves like this, it deflects it to the right, right? Air moves like this, wind speed decreases, but Coriolis is still active. So if here it starts to deflect this airflow to the right, okay? So if we start to draw a cross section here from point A to point B, let's illustrate the following. We're going to draw a cross section here from point A to point B, right? B, A, right? It's the exact same process. We draw a cross section. The top is 500 millibar. The bottom is 1000 millibar. Or surface, as 1000 millibar is representative of the surface pressure. And should you not know it by now, I mean, pressure decreases from the bottom to the top the higher you go up into the atmosphere, right? And we separate these 2 points here, right? Point A here and point B, right? Due to the deflection still happening where the Coriolis force is actually bigger than the wind speed, it gets deflected to the right. And due to this deflection here at point A, there's actually air converging here because of this deflection. This deflection converges the air here at 500 millibar, say 5,600 meters high above the surface. There's air now converging here due to this deflection, right? So here we have now a converging airflow high up above point A, right? And this sets up a whole set of motions on its own. Because since you have a converging airflow here, this airflow starts to sink downward towards the surface. And this is pretty evident also if you look at the brightness temperatures here in this region, right? It's super dark, right? So you have a super dark region here in the water vapor imagery, and dark features in the water vapor imagery are actually indications of sinking air, right? Now, because of the sinking air, there's again a secondary circulation that's induced at surface from A to B, right? Because this air is converging, it's going downward, and this air is now rushing here to point B. So it sinks here, and at surface, the air is deflected to point B. And since now there's air being rushing to point B here, right, you can see that there's actually divergence aloft, divergence at surface here, because of this convergence and sinking air, there's air leaving here towards point B at surface. And because there's air leaving here at point A, rushing to point B, there's massive convergence happening here at the ground, right? And convergence acts twofold, right? It pushes the air upward, right? So there's a rising motion here as evidenced here by the thunderstorm development, right? And because the air is now moving upward, the air at surface at point B weighs less because of the upward vertical motion. So there's actually pressure falls here at the surface. The pressure decreases, right? Leading to a potential formation of a low pressure center or the strengthening of an existing low if it's already present, right? And this convergence, if there's instability here, as you can see here, there's thunderstorms here, so there's obviously instability, right? This upward motion here at point B, upward, right, leads to as we already mentioned, formation or sustaining of a low pressure center or strengthening even of a low pressure center, but it can also lead to the formation of thunderstorms there or precipitation in general. Right? So now it's no longer in the exit region, or in the entrance region rather. It was point A where you should look for vertical motion. In the exit region, due to the convergence aloft happening by the imbalance here, where the Coriolis force is stronger than the wind speed, right? It gets deflected to the right, leading to this circulation here, all right? And since there's conversion here at the bottom or at the ground near point B, all this air is pointed upward, right? So we've now identified that it's no longer the right portion of the region, right? But it's the left exit region where meteorologists should look for when it comes to the assessment of thunderstorm development, precipitation development, strengthening or creation of low pressure centers, right? So we've now actually arrived at the ending of the video. We've discussed how and where you can have vertical motions as a result of a jet streak. The entrance region, it's the right entrance region. In the exit region, it's the left exit region. Now, I hope this video was helpful for any of you. If you liked the video, as I already mentioned, press the like button. I'd really like you to leave a comment in the comment section to share with me what you think was good about the video and what you think was actually less good about the video. The audio quality and the video quality, it will improve over time. My performance will improve over time as well. But as I already mentioned, it's my first video, so cut me some slack if you want. Yep, so that's it, I guess. So if you want to be notified of future videos, again, please subscribe and let's see each other in a future video. Bye, everybody.